Welcome to Quiet Car Stories. Tonight we'll be exploring the slow disappearance of the carburettor, a small mechanical device that shaped the sound, feel, smell, and personality of engines for most of the 20th century. For decades, carburettors controlled the delicate balance between fuel and air inside millions of vehicles around the world. They influenced cold starts on winter mornings, the rhythm of an idling engine, the sound of acceleration on open roads, and the small mechanical rituals that once defined driving. And then, slowly, they disappeared, replaced by quieter, cleaner, and more precise electronic systems that transformed the way engines behaved. In this documentary, we'll explore how carburettors worked, why they became so important, how they evolved through automotive history, and why they eventually faded away from everyday cars. As always, this episode is designed to be calm, slow-paced, and easy to listen to. Whether you're winding down for the evening, working quietly in the background, or simply relaxing with a love of old engines and automotive history, you're very welcome here. And before we begin, I'd love to hear from you in the comments. Did you ever own a carburetted car or motorcycle? Is there a particular engine, smell, or memory that still stands out to you? Perhaps the sound of a cold start on a winter morning, or adjusting a choke before setting off down a quiet road. If you enjoy these slow automotive documentaries, please consider liking the video and subscribing to Quiet Car Stories for more calm engineering and car history episodes in the future. Now, settle in, get comfortable, and let's begin. There was a time when almost every petrol-powered engine relied on a surprisingly simple principle. Air moving through a narrow passage could draw fuel into an engine. That was the foundation of the carburettor. No electronics, no sensors, no software calculations taking place invisibly in the background. Just airflow, pressure differences, springs, diaphragms, fuel, and carefully machined metal components working together mechanically. For much of automotive history, this system powered the world. The carburettor became one of the defining technologies of the internal combustion engine. Hidden beneath air cleaners and intake assemblies, it quietly controlled the mixture of fuel and air entering the cylinders. And although many drivers rarely thought about it directly, the carburettor influenced nearly every part of the driving experience. It affected how the engine started, how smoothly it idled, how sharply it responded to the throttle, how it sounded under acceleration, even how it smelled after a cold start. And perhaps most importantly, carburettors gave older engines much of the character people still remember today. To understand why carburettors became so important, it helps to go back to the earliest years of the automobile itself. During the late 19th century, engineers around Europe and North America were attempting to solve a difficult problem. Internal combustion engines required fuel and air to mix together before ignition could occur. Too much fuel and combustion became incomplete. Too little fuel and the engine would struggle to run properly. Finding the correct mixture under constantly changing conditions became one of the defining engineering challenges of early engine development. The earliest systems were extremely primitive. Some engines simply allowed air to pass over exposed fuel surfaces, picking up vapor as it traveled toward the cylinders. These systems worked inconsistently and were heavily affected by temperature, fuel volatility, and airflow conditions. Engines were often unreliable, cold starts were difficult, fuel delivery fluctuated unpredictably. As automotive engineering progressed, inventors began developing more advanced methods of mixing air and fuel. The carburettor emerged from this process gradually rather than through one single invention. Multiple engineers and manufacturers contributed to its development over time. The core principle behind the carburettor relied on what is known as the Venturi effect. As air flows through a narrowing passage, its velocity increases and pressure decreases. This pressure difference can then draw fuel into the airflow through calibrated openings known as jets. The fuel atomizes into fine droplets and mixes with incoming air before entering the engine cylinders. It is an elegant solution, simple in principle, yet surprisingly sophisticated in execution. Early carburettors quickly evolved beyond their basic beginnings. Float chambers were introduced to maintain consistent fuel levels. Throttle plates allowed airflow to be controlled mechanically. Additional fuel circuits handled idle conditions where airflow through the main venturi became too weak to draw sufficient fuel. Gradually, carburetors became more refined, more adaptable, and more reliable. By the early 20th century, they had become standard across much of the automotive world, and because carburetors operated entirely through physical forces, they gave engines a very different personality from modern electronically controlled systems. Modern engines are designed to minimize variation wherever possible. Sensors monitor airflow, temperature, throttle position, oxygen content, and countless other variables continuously. Fuel delivery adjusts instantly through electronic control units operating many times per second. Carburetors could not do this. Instead, they responded mechanically to airflow, vacuum, fuel pressure, spring tension, and temperature changes. As a result, carbureted engines often behaved slightly differently depending on conditions. Cold weather affected fuel atomization. Altitude altered air density. Humidity influenced combustion. Engines developed habits and quirks that drivers learned over time, and this created a stronger sense of mechanical familiarity between driver and machine. Starting an older carbureted engine often involved a small ritual. On cold mornings, many vehicles required use of a choke system. Restricting airflow enriched the fuel mixture, helping cold engines maintain combustion while fuel vaporization remained poor. In many older cars, the choke was manually operated using a pull cable inside the cabin. Drivers learned how much choke their engine preferred. Too little and the engine might stall repeatedly. Too much and excess fuel could flood the cylinders. A winter morning in the 1960s or 1970s often began with the sound of a starter motor turning slowly against thick, cold oil. The engine might cough once, hesitate, then gradually settle into a rough, uneven idle while warming up. The driver listened carefully, adjusted the choke slightly, waited for the engine to smooth out before pulling away. These small interactions created a sense that the engine itself was something alive and mechanical rather than simply electronic machinery operating invisibly beneath the bonnet. Modern cars rarely behave this way. Fuel injection systems automatically enrich cold, start mixtures with remarkable precision. Idle speed stabilizes almost instantly. Engines adapt silently to changing conditions without requiring driver involvement. Objectively, these systems are far superior, but they also remove many of the small sensory experiences that once defined older cars. Carburetors also shaped the sound of engines in distinctive ways. As airflow increased through the carburettor under acceleration, intake noise became part of the driving experience. Large, naturally aspirated engines pulling air through carburetors often produced deep induction sounds that rose naturally with throttle input. Multi-carburettor systems amplified these characteristics further. European sports cars fitted with Weber side draft carburetors developed sharp, aggressive intake resonance. British sports cars using SU carburetors produced smoother induction tones. American V8 engines equipped with large four-barrel carburetors generated deep intake roar as secondary barrels opened under heavy acceleration. These sounds were not digitally engineered. They were simply the natural sound of airflow itself. The carburettor became part of the engine's acoustic personality. And because older cars often had less sound insulation and simpler exhaust systems than modern vehicles, these intake sounds formed a much larger part of the driving experience. The carburettor also remained visually understandable in a way many modern systems no longer are. Opening the bonnet of an older carburetted engine often revealed a system that could be followed intuitively. Fuel lines entered visibly through brass fittings. Mechanical linkages moved directly with throttle input. Springs, diaphragms, and levers responded physically to airflow and engine demand. Everything remained mechanical and tangible. Modern engine bays are very different. Plastic covers conceal major components. Wiring harnesses and sensors dominate the visible layout. Fuel delivery happens invisibly through electronically controlled injectors operating beneath sealed intake systems. Again, modern systems are more efficient, more reliable, and cleaner. But carburetors belong to a period where automotive engineering still felt openly mechanical. As the 20th century progressed, carburettor technology became increasingly advanced. Manufacturers developed different designs depending on performance goals, fuel economy priorities, and regional driving conditions. In the United States, where large displacement engines became common, carburetors often focused on delivering strong, low-speed torque and high airflow under acceleration. Four-barrel carburetors became iconic during the muscle car era of the 1960s and early 1970s. Under gentle driving conditions, smaller primary barrels handled airflow efficiently. But under heavier throttle, larger secondary barrels opened mechanically or through vacuum operation, dramatically increasing airflow into the engine. Drivers learned to recognize this moment instinctively. The intake sound deepened. The engine suddenly felt as though it had begun breathing more freely. Power surged forward. This mechanical transition became part of the sensory experience of driving large carburetted V8 engines. In Europe, carburetor philosophy often developed differently. Fuel prices were generally higher. Engines tended to be smaller and more focused on efficiency and responsiveness rather than raw displacement. Multiple carburetor systems became common on sports cars and performance engines. Italian Weber carburetors became legendary for their throttle response and airflow capability. British SU carburetors gained reputations for smoothness and elegant simplicity. Solex carburetors appeared widely across European saloons and economy cars. Different carburetor designs developed distinct personalities. Some prioritized smooth drivability, others sharp throttle response, others fuel economy. And because all of these systems operated mechanically, tuning became deeply tactile and sensory. Mechanics often tuned carburetors partly by ear, idle speed adjustments, fuel mixture screws, synchronizing airflow between multiple carburetors. Tiny changes could noticeably alter how the engine behaved. Spark plug color provided clues about mixture strength. Exhaust smell indicated rich or lean running conditions. Throttle hesitation could reveal incorrect jetting. Carburetor tuning became almost an art form in performance applications. Racing engines throughout much of the 20th century relied heavily on carefully calibrated carburetor systems. Motorsport engineers developed extraordinary expertise in airflow tuning, vent resizing, fuel atomization, and throttle response characteristics. And because carburetors remained physically accessible, owners themselves often became more mechanically involved with their cars. Adjustments could be made manually, jets replaced physically, linkages altered directly. The engine's behavior remained tangible rather than hidden behind electronic software. This created a different relationship between driver and machine, not necessarily because older cars were better, but because they demanded slightly more awareness. Drivers learned the moods of their engines, how they behaved in winter, how they responded to damp weather, how altitude affected performance during long journeys through mountainous regions. Modern electronic fuel injection systems automatically compensate for these variables almost instantly. Carburetors could not. And that limitation became increasingly important as automotive priorities changed during the 1970s and 1980s. By the 1970s, the automotive industry was beginning to change in ways that would eventually make the carburetor difficult to preserve. For decades, carburetors had evolved successfully alongside engine development. Manufacturers refined airflow characteristics, improved fuel metering, and introduced increasingly sophisticated systems to improve drivability and efficiency. In many ways, carburetors had become remarkably advanced mechanical devices. But the world around the automobile was changing. Fuel prices became less stable following the oil crises of the 1970s. Emissions regulations tightened significantly in the United States, Europe, and Japan. Air pollution concerns pushed governments toward stricter exhaust standards. Fuel economy became increasingly important to both manufacturers and consumers. And gradually, the limitations of carburetors became more difficult to ignore. The central problem was precision. A carburetor responds indirectly to airflow and pressure changes. It cannot directly measure combustion conditions inside the engine. It cannot analyze exhaust gases continuously. It cannot instantly compensate for every environmental change with complete accuracy. Modern electronic fuel injection systems eventually could. As catalytic converters became widespread during the 1970s and 1980s, fuel control requirements became much stricter. Catalytic converters work most effectively when the air-fuel ratio remains within a relatively narrow range. Too rich, and emissions increase dramatically. Too lean, and drivability suffers while emissions performance declines. Maintaining this balance consistently under all operating conditions proved extremely difficult for purely mechanical carburetor systems. Manufacturers attempted increasingly complicated solutions to keep carburetors viable. Vacuum-operated emissions controls multiplied throughout engine bays. Electronic feedback carburetors appeared, combining traditional mechanical fuel systems with primitive electronic control elements. Oxygen sensors began feeding limited information into control modules capable of adjusting fuel mixture indirectly. By the early 1980s, some carburetted engines had become remarkably complex. Vacuum hoses spread throughout engine compartments in dense networks. Thermal vacuum switches, air injection systems, evaporative emissions controls, and electronically controlled solenoids all attempted to improve emissions performance while preserving carburetor operation. Ironically, carburetors had originally become popular partly because of their mechanical simplicity. Yet, toward the end of their mainstream life, many systems had become complicated enough that diagnosing problems could be surprisingly difficult. Despite all of this added complexity, fuel injection systems continued improving rapidly. Electronic fuel injection had existed in specialized forms for many years, particularly in aviation and high-performance applications. Mechanical fuel injection systems had appeared on certain racing and production engines decades earlier, but it was the rapid improvement of electronics during the late 20th century that truly transformed fuel injection into a practical mass-market technology. As computing technology became smaller, cheaper, and more reliable, electronic fuel injection systems gained enormous advantages. Sensors could monitor coolant temperature, intake air temperature, airflow, throttle position, engine speed, manifold pressure, and exhaust oxygen content continuously. The engine control unit could then adjust fuel delivery instantly. Cold starts improved dramatically, fuel economy increased, throttle response became smoother, altitude compensation became automatic, engines adapted to changing conditions silently in the background. From an engineering perspective, fuel injection solved many of the problems carburetors struggled with inherently. And so, during the late 1980s and throughout the 1990s, the transition accelerated. Carburetors gradually disappeared from new passenger cars across much of the world. The change did not happen overnight. Many economy cars retained carburetors longer because of manufacturing cost. Certain markets transitioned more slowly than others. Motorcycles continued using carburetors for many years after fuel injection became standard in cars. But the overall direction of the industry had become unavoidable. By the early 2000s, carburetors had largely vanished from mainstream passenger vehicles in most developed countries. And with their disappearance came a subtle but important change in how engines felt. Fuel-injected engines started almost instantly regardless of weather conditions. Idle quality became remarkably stable. Fuel delivery remained consistent across changing altitudes and temperatures. Engines no longer stumbled during warm-up or required careful choke adjustment on cold mornings. Again, these were genuine improvements. Modern engines are objectively easier to live with. Cleaner, more efficient, more reliable, but something of the older mechanical texture disappeared as well. Carburetted engines often felt alive in small ways. The engine changed slightly with weather and temperature. Cold starts felt mechanical and physical. Intake sound varied naturally with throttle position and airflow demand. Drivers became familiar with the engine's moods and habits over time. Modern engines are designed specifically to eliminate this variability, and in doing so, they often feel more isolated from the raw combustion process itself. The relationship between driver and machine changed gradually during this transition. Older carburetted cars frequently encouraged mechanical awareness simply because the systems remained visible and accessible. Drivers often carried small toolkits. Idle adjustments could be performed manually. Carburetors occasionally required balancing, cleaning, or tuning. Engines communicated their condition through sound, smell, vibration, and behavior. Modern vehicles intentionally minimize this kind of interaction. The goal became seamless operation. The engine should simply work, quietly, reliably, predictably, without demanding attention from the driver. And from a practical perspective, this philosophy succeeded remarkably well. Today's engines routinely achieve reliability, efficiency, and emissions performance that would have seemed extraordinary during the carburetor era. Yet, carburetors continue to occupy a special place in automotive memory. Not because they were perfect. They certainly were not. Poorly adjusted carburetors could create terrible drivability. Cold weather operation could be frustrating. Fuel economy often suffered. Emissions were unquestionably worse than modern systems. But carburetors represented a different kind of engineering relationship. One where the mechanical process remained tangible, visible, understandable. You could often hear the airflow changing through the intake, smell excess fuel richness during startup, observe throttle linkages moving physically beneath the bonnet, adjust fuel mixtures using a screwdriver rather than diagnostic software. This analog quality became deeply tied to how older cars felt emotionally. And perhaps that emotional connection explains why carburetors remain so fascinating to enthusiasts today. Classic car owners still spend careful afternoons balancing carburetors and adjusting idle mixtures. Vintage motorcycles continue relying on beautifully simple carburetted systems. Restorers rebuild worn carburetors with extraordinary attention to detail, cleaning jets, replacing seals, polishing housings, and carefully resetting float levels. When those engines finally start and settle into a steady idle, the experience often feels deeply satisfying. Not because the system is technologically superior, but because the process feels mechanical and physical in a way modern electronic systems rarely do. Even the sounds associated with carburetors remain distinctive. The soft induction hiss of SU carburetors, the sharp intake bark of Weber side drafts, the deep roar of American four-barrel carburetors opening under acceleration. These sounds belong to a different era of engine design, an era before extensive sound insulation, electronic throttle mapping, turbocharged downsizing, and digitally controlled intake systems reshaped the acoustic character of modern engines. Today, younger enthusiasts often encounter carburetors almost as historical objects. Opening the bonnet of an older carburetted engine can feel surprisingly different from looking into a modern engine bay. Mechanical linkages remain visible. Fuel delivery appears understandable rather than hidden beneath layers of electronic management. There is a kind of honesty to older carburetted engines. You can often follow the airflow physically from intake to combustion chamber. That visible mechanical process creates a stronger sensory connection between person and machine. And perhaps that is ultimately why carburetors continue to inspire nostalgia far beyond their actual practical advantages. They represent a period where engines still felt openly mechanical, a little imperfect, a little temperamental, but also deeply tactile and expressive. As electric vehicles become increasingly common, the disappearance of carburetors now feels even more distant. The gap between a modern electric drivetrain and a carburetted engine is enormous. One operates almost silently through software-controlled electric motors and battery management systems. The other relies entirely on airflow, fuel pressure, springs, diaphragms, and carefully balanced mechanical circuits, and yet both belong to the same long history of transportation, separated not by a single invention, but by decades of gradual evolution. Looking back now, the slow disappearance of carburetors mirrors many broader changes throughout automotive history. The movement from analog systems to digital systems, from mechanical interaction to electronic management, from visible engineering to invisible software, from tactile imperfection to seamless precision. And like many important changes in engineering, it did not happen suddenly. It happened quietly, gradually, almost unnoticed, until eventually the carburettor became something associated more with memory than with modern roads. But even now its influence remains, in the sounds people still remember, in the smell of fuel lingering in old garages, in the feel of vintage engines warming slowly on cold mornings, and in the stories shared between generations of people who remember when driving felt just a little more mechanical than it does today. Thank you for spending time with Quiet Car Stories. If you enjoyed this documentary, you can support the channel by liking the video, subscribing, and sharing your own memories of carburetted cars and engines in the comments below. And for now, wherever you are in the world, I hope this episode helped you slow down for a little while. Good night.